We will understand code and how to code large concept models by Meta AI. This is their GitHub repository, and I'm trying to make a smaller version of this model so I can train it first on the free Google Colab GPU and then maybe rent some better GPUs. This could be on the path towards superintelligence, because here, instead of predicting the next token, we predict next entire sentence. So sentences are a lot more rich, so we improve the computation a lot here because they contain a lot more information. So I want to understand both the concept of training this and the architecture and the engineering behind it. After understanding this, I will be able to understand next steps a lot better. You can follow everything I do on my channel. So I've done all of the data preparation and data loading, which will also come out in a video, and next I want to code the architecture of the model. Once we understand this code, we can do a lot of optimizations, like all of the DeepSeek's optimizations, Muon optimizer, and Triton and CUDA kernels and stuff. So let's start from this LCM neural networks transformer factory. So this is factory for the transformer. We see code here, so let's see what it does. So this defines a modular transformer decoder layer factory tailored for flexibility and advanced research, especially for experiments involving variations in attention, normalization, and positional encodings. So we can do experiments with a lot of different modules here. We can choose which ones we want to try out against the other ones. It's built on FairSeq2. This is the module. This is another repository on GitHub. Meta sequence modeling framework, and incorporates custom enhancements from LCM. So this is what they coded in this large concept model specifically. So they use both this pre-made template and their custom modifications. So this is the repository if you want to check it, fair sequence 2, but I will be coding everything from scratch because we need to do optimizations, we need to understand how it works and maybe make improvements to the mechanism. So first we have this transformer config data class. So this will just keep this data, hyperparameters, number of layers, attention, number of attention heads, dropout stuff, and other stuff like normalization, positional embeddings, feed-forward network, use, swig-glue, inner dimension, etc. For example, position embeddings can be rope, sign, learned, or none. And the default is learned. So this is interesting. It looks like this is all for experimentation. So they do experimentation with all of this stuff. Maybe we will do something like this, maybe not. We'll see. But now we just want to understand. So this second transformer factory builds the actual layers based on the config. So there is this build layer function, and it creates transformer decoder layer using custom multi-head attention that is built by this build attention, and then feed-forward network, optional residual scaling, normalization, custom decoder layer class. Yeah, this is a custom class for the layer as well, for the decoder layer. So we will learn more about all of this. So we have our build positional encoder and build attention positional encoder. This will decide if we are using learn, sign, or rope, or none. So for example, when it's building this standard feed-forward network, it's actually just instantiating this class. And this class is imported from this from this NN transformer from fair sequence 2. But we will build all of this from scratch. So I think we don't need to worry too much about this, because I will show you on my channel when we build all of this from scratch, you will understand the architecture. So I'm not interested in looking how it works here, because we will not do it like this. So first it says here, the model's embedding layer will be replaced by a simple linear layer to project from SONAR space into the model embedding space, model dimension, okay. And then LM head will be replaced with this linear layer as well, that will go from model dimension to the SONAR space. So the input is not going to be taking token IDs, but a sequence of pre-computed SONAR sentence embeddings. So tensor of shape number of sentences 1024, which is shape of one sentence embedding vector. And then the biggest change is the diffusion process. So during training, you won't just feed the model the correct next sentence like we do with correct next token. You will take the ground truth sentence embedding, add noise to them according to a noise schedule. The amount of noise depends on a randomly sampled time step t. Okay, so we will not always give the same time step like 100. We will give a random time step. You can learn more about time steps in this full course, Coding a Diffusion Transformer from Scratch, so watch this video. We will be doing the same thing here, almost the same. Feed the model the context, previous sentence embeddings, and the noisy target. What? I guess we feed the noised out version of the sentence. And there should also be a timestamp, like some number, or that's gonna tell how much noise there is to the model. Yeah. The model's new job is to predict the original clean sentence embedding, or equivalently, predict the noise that was added. The loss function will be the mean square error between the model's prediction and the clean target. I don't know about this. We already have this mu on loss. Oh, actually, no, mu on optimizer. Never mind. Okay, mean squared error. So now Gemini generated this noise scheduler for me. So let me check it out. I see we already explained in my video here, and then diffusion from scratch, which is even a simpler version. So I think we will just copy this for now, and if there are any bugs later, we will find bugs and try to understand this even deeper. Or when we are optimizing it later, we will understand it even deeper. And then the time step encoder, we cannot just give it a single number, we need to encode it into a vector. So I explained that as well. We will just copy this as well. So I'll copy it into this block and run it. We have some issues. NN is not defined. Okay. So import torch.nn as nn. Then we will modify the GPT class and we'll rename it concept model to reflect its new purpose. So originally, my GPT class is just creating this GPT architecture. It has this forward, and this is written by Evin and other people. This guy, you can check his channel here as well. So there is just this classic transformer, normalization and stuff. And then generate function, and that's it. So key changes: remove NN embedding and the value embeds. We are not using token IDs anymore. Add input projection and output projection, linear layers to go from and to SONAR dimension and the model dimension. Add timestep encoder, an instance of the class we just defined. Modify forward method. It now accepts a noisy target, context, and timestamps. It combines the timestep embedding with the context before feeding it to the transformer blocks. Remove generate method. Inference is now a multi-step denoising process and will be handled outside the model. So I guess I'll just copy this code without understanding it. Well, let's copy, let's see what happens, and then we will debug and stuff. So I guess I will first copy my entire code until the GPT class, because we need these dependencies and stuff. So I will run it. We have problems again. Kernel is not defined. I'll just take my whole kernel.py file. So it's a /GPT lab. And let me just copy that somewhere. So I'll put this file here, run it. And now we don't need to import this from kernel. Here we don't need to import this. I'll comment this. We will just have it. Okay, what is this now? We are not on CUDA runtime, which is a bit annoying. I don't know what to do about this. So I'll try to comment it and see if it's gonna compile. No. I guess let's change runtime type. Save. We will now use GPU. So I don't know what I even did here. Let's go here. These would be our kernels. And then I will uncomment this and run it. Now still doesn't work. No module name, what? I just commented. Oh, my bad. Not this one, but this one. Okay, let's see. Now another error, same thing. So here we are parsing the arguments from command line, but we don't want that. We just want, in Google Colab, we just want to directly read. We can define hyperparameters here. So that's what I did. So now I added actually my code that I created as well, which is I implemented DeepSeek's multi-head latent attention here. This is my class. I copied a bunch of stuff from DeepSeek, but I also made the whole model work with it. So we will use this instead of the flex attention that the original, that Evan's repo used. So it ran properly. Now let me do this. So this will throw an error here. I think I will just say MLA. And now different problems. I just need to define this world size is equal to 1. Now we have different problem. There is no max batch size. Here we have a mini DeepSeek v3 with MLA latent attention training on free Google Colab. So this is the code. I coded MLA and other parts of code are from other people. There is a bunch of people. So actually Gemini was able to fix a bug, one-shot a bug that I didn't even know how to fix, which is I just pasted my whole code and the bug and it just fixed it. It's crazy. This latest Gemini from 6th month, from 20 days ago, is absolutely crushing everything else. Especially you see here web development. So I guess even in Python could be better. And it's almost gonna reach 1500, one of the next iterations here on text. So this is why I talk about super intelligence and not about the general intelligence, because first of all, humans are have very specialized, narrow intelligence for moving arms, moving legs, and this stuff. So expecting AI to be exactly the same as human is not general, and we don't have data, so it will probably become super intelligent in coding and math before it becomes even human level in maybe some other things that are humans really good at. So those big numbers, b float 16, cannot be represented in float 16, so they just become infinity. So that's why this bug was happening on Tesla T4, where it simulates when it doesn't have actual b float 16. So my original code was actually this LM head. This is doing in b float 16. So what Gemini said is, instead of doing it like this, we will convert this to float 32. So we replaced this whole thing. So we created a new linear layer, which is actually same as this LM head. It's also defined earlier in the code as linear layer, but we will define it actually here again. And input, it will be this X float. So we will convert our input to actual float. So this is b float 16. We will convert it to float. So I'm not sure why it says here float 32. Yeah, so dot float is same as is float 32, and half would be float 16, and b float 16 would be b float 16. Okay, so we convert to float 32 instead of float 16 or b float 16, and then the weights also. So self LM head weight convert to float 32, and then this will not do calculations in bflow 16 simulated, but in just bflow 30 in float 32. So that resolved the bug. I now ran the training, so these are the model hyperparameters. You see it's very small walkup size 1000 and model dimension 124, so it's small. And you see here we have 20 test steps, and it all works, so each of them takes about 5 seconds. And so our training works, and I have successfully implemented multi-head latent attention from DeepSeek into this GPT architecture. That's, I don't know if it's even GPT anymore because it has been changed a lot as well. But this is a small model that can be small LLM that can be pre-trained on a simple GPU or a few GPUs. I asked Gemini how to improve my training speed. You know, it takes 5 seconds per step. Actually, it says here to remove bfloat 16 because it needs to be simulated in FP32 because T4 doesn't have it. So we should use FP16 and that's it. So I made a new branch optimizations that's from main, and then we will do optimizations here, and I changed my collab here to optimizations and pulled it. So let's implement this. So we will use this autocast to automatically cast operations to FP16 where safe and beneficial. This so that's autocast, and also GradScaler helps prevent gradients from becoming zero, underflowing, when using the smaller FP16 range, because FP16 is a smaller range than BF16. So it tells me to use this max autotune on the compilation, but instead of reduce overhead. A reduce overhead is good for testing because it quickly compiles, and max autotune is when you want to really start training, so it takes more time but makes everything faster. But we don't want that, so I'm gonna keep it at max at the reduce overhead because I'm still testing and I want to just try FP16 for now. So here we will initialize this GradScaler, which seems to be deprecated. So we will do it this way because it tells us to do it this way: torch, amp, GradScaler, and passing CUDA. That's the only thing for now we will do. Then we will actually wrap this forward pass like that. And this is also deprecated, so we can just use it like this instead. I think it will work. But this is also, oh my god. So you say torch, amp, autocast, CUDA like this. So I'll do it like this. Oh, it's gonna be tough here. I think like that. Yeah, if I hover over, it says device type, which is CUDA, and then D type and all this good stuff. So I could even do it like this. Then instead of loss backward, we will comment this and we will do it like this. And let's see, there is no deprecation warning, so I think this is good. So we will scale loss, it seems. It says here if we are using more than one GPU, we need to unscale gradients before all reduce. If you use GradScaler with DDP, I don't know what DDP is, and we are using just one GPU, so I guess let's not do any of this. And now, where we step the optimizers with 4 in opt-in optimizers, we will not do it like that. We will instead copy this scaler.step optimizer 1 and optimizer 2. And we will also scalar update the scaler for the next iteration. Like that. So now I will just commit this file and push. And here I need to go here and then pull from GitHub. One file changed and then start the training. So it was 5 milliseconds. Let's see if we have, it was 5 seconds per step. Let's see what happens now. And maybe we will also have bugs. So we again have bugs with underflowing now. or overflowing. I think it's underflowing. So this matrix multiplication produce two small values, so they just become 0 because they cannot be represented in FP16. Sorry, so yeah, it is FP16. So first, there are conflicts with this FP8. So let me just remove this FP8 so we don't use it, okay? It also wants us to remove this CastedLinear class entirely. So I guess let me comment it. I just commented out entire CastedLinear layer. So that was just for multiple GPUs, but we have one GPU. So then I will just use NNLinear here instead of the CastedLinear. I replaced that. And I added these few lines of code, maybe to keep the numbers stable between these bounds or something. I'm not sure exactly. It was all recommended by Gemini, yeah. Then I will replace in the GPT class this entire LM head. So it has a bunch of this stuff. I will just put this as Gemini said. I guess it also wants me to add this. So I guess I'm gonna comment out this one and just put it here. Maybe it does the same thing. And then here in the GPT forward, I need to remove float because it says here that it could be harmful. It also says that we can unscale gradients if before the step, like that. I guess I'll keep it like that. This corrected flow ensures that Muon optimizer, our custom optimizer, receives proper unscaled flow 32 gradients to work with, preventing the internal matrix math from producing nonce. Replacing the incompatible CastedLinear removes the initial source of the problem. And here, in the linear layer, we say D type is bfloat16. We want to comment that out. We don't want that. And then I need to remove this reference to linear D type because it doesn't exist anymore. This is very interesting. DeepSeek researcher just released their side project, Nano-vLLM. It's for fast inference, so I've been checking like some of these files. And then schedule. It returns tuple, which has a list of sequences, and bool. This is the core scheduling algorithm. It tries to batch and run as many sequences as allowed by resource limits. Then this part, for new sequences, waiting queue, checks if it can fit within maximum number batch tokens, tries to allocate KV cache via block manager. If okay, mark it running, move it from waiting to running, and track it in scheduled sequences. So it just checks the length of the new sequence, and it checks if it can be added, and then it adds it to the sequence. So return early if any prefill. We have this scheduled, if scheduled steps, return scheduled steps true. If any prefill was scheduled, return early, caller can process those. So I think prefill is like calculating KV cache until of the context window of the text that's sent by the user before it starts generating next token. That will be this code. And then after we have this decode. There is also this preempt function that will move running sequence back to waiting and free its KV cache and add it at the front of the waiting queue for quick rescheduling.